Is it visible to you? Is the screen visible? Okay, okay, Alish, okay. Anurag, okay. So, today we are going to start the next part of the recurrence solving recurrence relation. That is how to solve non-homogeneous recurrence relation. Okay. Earlier classes we saw how to solve homogeneous recurrence relations. Now we are going to see how we can solve non-homogeneous recurrence relations. What are non-homogeneous recurrence relations? What are non-homogeneous recurrence relations? Come on fast. What are non-homogeneous recurrence relations? Anyone? So you should write all these questions in your notebook as I am writing it down, okay? I won't be covering all questions in the note. So whichever I'm solving now, you will have to write it down in the notebook. Very good, Niharika. What is not zero? The right hand side of the recurrence equation is not zero. So not zero means it can be a constant, it can be a polynomial of degree n, it can be an exponential function, etc. So we have to look at different cases. That is, if it is a constant instead of zero, if it is a constant, how will we solve the recurrence relation? And if it is zero, if it is a polynomial on the right hand side, how can we solve? Then if it is an exponential, if it is an exponential form like a raised to n form, how can we solve the recurrence relation? So depending on the right hand side, whatever is written on the right hand side, we have different methods for solving. Okay, so here we are going to solve solution of, write the heading, solution of non-homogeneous recurrence relations. Solution of non-homogeneous recurrence relations. And we are using the method using, initially also, we were using characteristic root method. Okay. For solving homogeneous recurrence relation also, we had used this method because we found the roots, isn't it? We had found the roots and then we substituted. So that method is finding roots and then finding the solution of the recurrence relation is called characteristic root method. So if you're going to find the roots and solve the equation, it is called characteristic root method. So until now, we were following the characteristic root method. Okay. So let us see how this equation looks like, the general form. Okay, general form of the recurrence relation, general form of recurrence relation. General form of the recurrence relation is given by a constant C0 into An plus C1 into An minus 1. This is what we were solving till now, isn't it? Plus etc. Ck An minus k is equal to, if it is equal to 0, then it is homogeneous. But what we are doing here, we are considering non-homogeneous equation. So this right hand side will not be 0. Instead of that, we can have a function f of n, and f of n can take different forms. Okay, it can be f of n. Okay, this is the general form of a non-homogeneous recurrence relation where the right hand side is not 0. Instead, it is a function of this n. Okay, is it clear? So this is the general form of a recurrence relation which is non-homogeneous. This is non-homogeneous because this right hand side is not 0. It is a function of n. Is it clear? Did you, if it is homogeneous, then this right hand side, this the same formula, that is C0 an plus C1 an minus 1 plus etc. Ck an minus k, but it will be equal to 0 on the right hand side. But if it is a function of n, it is not 0. It is, we have some function of n is defined on the right hand side, then it becomes a non-homogeneous recurrence relation. Now let us find out how what is the general solution of non-homogeneous recurrence relation. The general solution, that is the n solution that we want to get, the general solution in terms of n, we will be finding the final solution, isn't it? So general solution is of the form an is equal to an homogeneous solution plus an particular solution. This is the general form. You have to learn this. This is the basic formula that we are going to substitute to get the general solution. An is equal to an homogeneous solution plus an particular solution. So here we see that the general solution of non-homogeneous recurrence relation is the sum of its homogeneous solution and its particular solution. It is the sum of two solutions. The general solution of non-homogeneous recurrence relation is the sum of two solutions. The first solution is the homogeneous solution, second solution, and that is what we write it as H, homogeneous solution. And second, this is not power, okay, this is just showing that it is the homogeneous solution. And the next part of AN is the particular solution, Pn. So if we find homogeneous solution and particular solution, if we add them together, we get the general solution. So our aim to find, in order to find the general solution, we have to first find the homogeneous solution, then we have to find the particular solution, and then we take the sum of the two. Is it clear? That this is the basic method to solve a non-homogeneous recurrence relation. To find this is the general solution of a non-homogeneous recurrence relation, and the general solution of a non-homogeneous recurrence relation is given by the sum of, it is the sum of the homogeneous solution and its particular solution. Okay, so the general solution of homogeneous recurrence relation is the sum of the homogeneous solution and its particular solution. So this is the basic idea behind this. So we know what we had found out, how to solve or how to find homogeneous solution in the previous examples. The same method is used to find homogeneous solution here also, but in addition to finding the homogeneous solution, you have to find a second solution also, and that is called particular solution. So this homogeneous solution, we get it corresponding to the LHS. We get homogeneous solution because when we equate LHS to 0, this becomes homogeneous equation, recurrence relation, and then we solve it the same way as we had done before and find the homogeneous solution first. Then when we solve the RHS, because we know RHS is not 0 now, so when we solve RHS, we get particular solution. And when we add these two together, we get the general solution. Is it clear? So we have to solve both the left hand side and the right hand side. Left hand side is same as what we had solved before, just like a homogeneous solution. How we found the general solution for a homogeneous recurrence relation, we have to solve the left hand side. And right hand side, we have a method. We have methods for solving the right hand side, and the solution that we get after solving the right hand side is called the particular solution. And when we add these two solutions together, we get the general solution. When we add the homogeneous solution and the particular solution together, we get the general solution of non-homogeneous recurrence relation. Is it clear? Any doubts in this? Is it clear? Do you have any doubts? Hello, you have to write it down, okay? Because I am going in a particular order. It may not be followed in the note. If you understand what is going on in class, then you will be able to understand the notes. Okay. Any doubts? Okay, Adarsh. So now let us take an exam. So we know this is the general form of the recurrence relation, and here this f of n can take different forms. Okay, and based on the different forms that f of n can take, we have different cases to solve. Okay, we have to solve it in different ways. And what are the different cases that can arise, or what are the different forms of f of n? Let us move on to case 1. Case 1. When the function f of n is equal to a constant. How will we solve the non-homogeneous recurrence relation when f of n is a constant? Say it can be 1 or 2 or 3, etc. on the right hand side. There is no dependent variable. They are just constants on the right hand side. Okay. For example, you have a's a n minus 1 plus or an plus an minus 1 is equal to 1. Okay. An plus an minus 1 is equal to 1. So if it was 0, we could have applied the homogeneous method, but here it is equal to a constant 1. So we cannot apply the other method. So what we have to do is we have to find homogeneous solution corresponding to the right hand side by equating this right hand side to 0. When you equate this side to 0, it becomes a homogeneous recurrence relation, and by equating it to 0, you can solve the LHS. Okay, left hand side can be solved. This is LHS. So you solve this left hand side by equating the left hand side to 0. It becomes homogeneous equation, and solve it using the method we had done earlier. And then you solve the next part, and you get the particular solution when you solve the right hand part. So how will we solve if it is a constant? That is what we are going to look at. Okay. So case 1, when f of n is equal to a constant. When f of n is equal to constant, the steps that we should follow is, first, you have to put p in the given equation. Put p in the given equation and find the value of p. Okay, the given equation means you will be given a non-homogeneous recurrence relation in the question. In that equation, we have to put p and find the value of p. Second, if you are unable to find the value, if we will see what are these steps when we solve question. If it fails, put an is equal to np. Sorry, put an is equal to p. Okay, put an is equal to p first. Then if it fails, put an is equal to np, and again fails. Again, if it fails, then put an is equal to n square p, and so on. Okay, until you get find the value of p, you have to repeat this process if the function f of n is equal to a constant. So let me solve one problem so that you will be able to understand it. So anyway, note down this step, okay? If f of n, the right hand side is a constant, you have to put an is equal to p in the given equation and find value of p. P is a constant. Then if it fails, then put an is equal to np and try to find the value of p. Again, if it fails, then put n square p, and this goes on until you get the value of p. Okay, just note down the steps. When we do the problem, you will understand. Did you write it down? So which case are we going to solve? When you have a constant on the right hand side, isn't it? Isn't it? It is a non-homogeneous solution. Non-homogeneous solution can have different functions on the right hand side. If the function is a constant, these are the steps followed. Okay. Shall I proceed? Now write down the question. Solve. We are solving for case 1. Okay. Solve an minus 2an minus 1. This is our given equation 1. This is the question given. Okay. So how are we going to solve this problem? We find that the left hand side it is an terms, and on the right hand side it is not 0, it is a constant 1. So we have to, this is a non-homogeneous recurrence relation, and we have to solve this non-homogeneous recurrence relation by finding the homogeneous solution and the particular solution. We have to find two solutions, that is an of h. This is the homogeneous solution, and second one you have to find is an of p, that is the particular solution, and you get the general solution is, then the general solution is solution an is equal to an of h plus an of p. Okay, an of h plus an of p. So we have to find an of h and an of p. Now an of h means the homogeneous solution. An of p is the particular solution corresponding to the right hand side. Okay, so step 1, we are going to find out homogeneous solution. Find homogeneous solution an of h. This is the step 1. So to find the homogeneous solution, we had done examples earlier. An might write this question, but equate it to 0. Homogeneous solution always have 0 on the right hand side. So an minus 2 into an minus 1 plus a into n minus 2 is equal to 0. Isn't it? I am not bothered about the right hand side here. I'm going to find out the homogeneous solution using the left hand side alone. And I'm taking the left hand side and equating it to 0. It becomes a homogeneous equation. Isn't it? Now this has become a homogeneous equation, recurrence relation. And when I solve this, I will get the homogeneous solution first. Isn't it? So how are we going to solve? How will we solve? Put an is equal to r raised. We are going to find out the roots, isn't it, using characteristic root method. So just you write an is equal to n, you substitute an is equal to r raised to n, just we had done earlier. How will we write the characteristic equation? Just put r instead of a and raise it to the power of n. That is r raised to n minus 2r raised to n minus 1 plus r raised to n minus 2 is equal to 0. And from this equation, we are going to find out the roots, isn't it? To find out the roots, what you are going to do? Divide the entire equation by the lowest power of r, isn't it? R raised to n minus 2. The lowest term, r raised to n minus 2. So what will you get? R square minus 2r plus r is equal to 0. Isn't it? What we did? Divide by r raised to n minus 2. When we divide by r raised to n minus 2, you get this one. This is the characteristic equation. So next step, what we have to find out? What we have to find out in the next step? What is the next step? I'm solving the homogeneous equation, which we had done earlier. R square minus 2R plus R is equal to 0. This is what we got now. So how will we find the root? How are you going to find the roots? Or did anyone find the root? If you had found out the root, please post the answer in chat. Very good, Typhel. 1. How did you find it out? Root is equal to minus b plus or minus root of b square minus 4ac by 2a. When we solve this, you will get it is equal to, you get two roots, 1 comma 1. Isn't it? Two same roots. So you have two same roots. Then what is the equation for homogeneous solution? What is the equation for an of h? An of h, if you have two same roots, then the equation is c1 plus c2n into r raised to n. This is the general equation. This is the homogeneous solution if you have two same roots, where c1 and c2 are constants. Okay. Is it clear? This is the equation for homogeneous solution if we have two same roots. So this becomes a homogeneous solution. We have R as 1, isn't it? We have found out the value of R as 1. So we will substitute all these values at the end. We are not going to find out C1, C2 here. If initial conditions are given, we can find out C1 and C2. But in the question, I didn't give any initial condition. If initial conditions are not given, then you just put it as C1 and C2. But if initial conditions are given, you have to find, that is if A0 or A1 and A1 are given, then you have to find A0 first by putting n is equal to 0, then find A1 by putting n is equal to 1, find the constant values and then substitute here. Okay, now I haven't given any initial conditions, so just put it as such. So now we have found out the homogeneous solution. Okay, the general form of the homogeneous solution. Now next we have to find the particular solution. So by substituting this one here, you will get the homogeneous part. Okay. I will substitute it at the end. Or if you want, you can substitute here also. That is equal to C1 plus C2n into 1 raised to n. R is equal to 1. So you get C1 plus C2n into 1 raised to n. R we have got it to be 1. Okay. Then this is a homogeneous solution. Next, what we have to find? We have found one part of our solution, and that is homogeneous solution. Now next part is what we have to study as a new part, isn't it? We have solved homogeneous solution before, but particular solution we haven't found before, isn't it? Now let us see how to find. So step 1 we had found the homogeneous solution, and in step 2 we are going to find particular solution. We are going to find the particular solution. Okay. In step 2, we are going to find the particular solution. Now, to find particular solution, as we discussed earlier in the above step, I told you we have the equation given to us is equation number 1. I think you might have numbered it, isn't it? The equation given is an minus 2an minus 1 plus an minus 2 is equal to 1, isn't it? This is the equation given to us. This is equation 1 that is given in the question. Now, to find the particular solution, what we have to do is, the steps are given, isn't it? I told you the steps. What we have to do, if it is a constant, we have a constant on the right hand side, you put an is equal to p and try to find the value of p in the given equation. And so I had written the given equation, that is the given question, and put what? The first step says that put an is equal to p in 1. Okay, in this given equation, you put an is equal to p. Here to put an is equal to p, just change the an terms to p. Okay. First step, you just change the an terms to p. So what will this become? P minus 2p plus p is equal to 1. Just put, in the first step, you just substitute the an terms to p. Okay, in this equation. So you get p minus 2p plus p is equal to 1. On solving this, okay, when you are asked to put a n is equal to p, just change these a n minus 1, a n minus 2 terms to p. So, what is the answer? What will you get when you solve this? What will you get when you solve this? Solve this equation. P plus p minus 2p. What will you get? 2p minus 2p is equal to 1. Isn't it? What is 2p minus 2p? What is 2p minus 2p? Nobody knows? See, come on first. What is 2 minus 2? 0. So 2p minus 2p is 0. And I get 0 is equal to 1. Is it true? Does the rule does the rule satisfy these conditions of the left and right hand side? No. So we can write here the rule fails. Okay, the rule fails because 0 is not equal to 1. So our case 1 is here. Isn't it? We have told here. That is, find the value of if fails, then put a n is equal to np. When we put a n is equal to p, the rule failed. Isn't it? When I put a n is equal to p, the rule failed. So if it fails, then put a n is equal to np. Isn't it? So next I'm going to try with NP. Instead of putting P, I'm going to put NP. Here I had put AN is equal to P and the rule failed. So next step, the method says that if it fails, then put AN is equal to NP in equation 1. Isn't it? AN is equal to NP in equation 1. Now what is equation 1? AN minus 2 a n minus 1 plus a n minus 2 is equal to 1, isn't it? So in this equation, I am going to put NP. So just see, instead of AN, I am going to put NP instead of AN. So this becomes NP minus, next time when you write, you just say 2 into, okay, when you write the next time, you put it as 2 into n minus 1p. Okay, earlier we put it as NP, P for everything. So for the next term, we have to put n minus 1p plus n minus 2. This suffix n minus 2p is equal to 1. Okay, initially in the equation, we had put p for all an terms. Next, we have to put, when an is equal to np, you just write the suffix term here and then multiply by p. That is, np is equal to minus 2 into n minus 1p plus n minus 2p is equal to 1. Now, when you solve this, what will you get? Open the brackets. np minus 2n minus 1 into p. You get 2np plus 2 into 1 into p, you get 2p plus np minus 2p is equal to 1. Isn't it? Now here what will you get? What will you get here? This plus 2p and minus 2p will cancel. Then np plus np, you will get 2np minus 2np is equal to 1. Again, these 2 will cancel, get 0 is equal to 1. Again, the rule fails. Isn't it? Even the second time also, when I put an is equal to np, again the rule fails. That is what the second step says. Here, if it fails, put an is equal to np. And for me, in this question, the rule had failed, isn't it? So I have to put, the next time I have to put an is equal to n square p. Okay. So next what we are going to do, in the same equation, we are, instead of an is equal to np, I am going to put an is equal to n square p. That is an minus 2 into an minus 1 was a question, plus an minus 2 is equal to 1, plus an minus 2 is equal to 1. Here in this put an is equal to n square p, isn't it? P is a constant, okay. Put an is equal to n square p, then what will you get? Instead of an, I'm putting n square p minus 2 into n minus 1. Instead of n, you put n minus 1 square p plus n minus 2, the suffix 2, and you write the square. N minus 2 square p is equal to 1. Okay. When you solve this, what will you get? Solve the equation. Solve this equation. When you solve this equation, you get n square p minus a 2 into a minus b the whole square. What is a minus b the whole square? A square minus 2ab plus b square into p plus, again a minus b the whole square. A square minus 2ab plus b square into p is equal to 1. Isn't it? Now you solve this entire equation. What will you get the value of p? Will you get the value of p? Just check. When you solve this equation, what you are going to get? I'll give you 1 minute. Please solve and find the answer. Open the bracket and find the answer. Okay. When you solve this anyway, I'm not going to waste time. When you solve this equation, you will get 2p is equal to 1 or p is equal to 1 by 2. Did anyone get this answer? Did anyone get this answer? Very good, Taifel. Very good. So you are doing it fast. Those who get the answer, just post it, okay, in the chat box. So you get p is equal to half. So our aim was to find this constant p, isn't it? So now what is our particular solution? Our particular solution, an of p is equal to n square p, isn't it? When we put n square p, we got the value of p. So an of p is equal to n square p, and we found out the value of p. Now what is the value of p? We got it as half. So this is equal to n square into half. So the particular solution we got is when we substituted n square p for an. So you just and we found the value of p also. So the particular solution an is equal to n square into half. Now we got the particular solution. Earlier we found the general solution also, the homogeneous part also, isn't it? Here we found the homogeneous solution. An of h we had found out. It is this, and we had found out an of p. Now, what is the general solution? Thus, the general solution. Thus, the general solution is an is equal to an of h plus an of p. Okay, and that is equal to, we have found out an of h as c1 plus c2 n, isn't it, into 1 raised to n plus, what is an of p? An of p we have found out now, that is n square into 1 by 2. Okay. Is it clear? Hello? Is it clear? Any doubts? Suppose, so we had found out the general solution, but now we see that there are two constants C1 and C2 here. So to find the C1 and C2, we need the initial conditions, but it was not given in the question earlier. So suppose if I'm giving you the initial conditions also, that is given the initial conditions, given the initial conditions, A0 is equal to 2. Okay, given the initial condition A0 is equal to 2. Now we can find out the value, isn't it? Let us see how to find out the values. Put n is equal to 0. When we put n is equal to 0 in the equation, we had found out right now. That is, we had reached the general solution here, isn't it? This is a final solution. Now we are going to solve for these two constants in the final solution. So when we put n is equal to 0, you get, now the equation is, putting it in, an is equal to c1 plus c2n into 1 raised to n plus our particular solution n square into 1 by 2. Now when we put an is equal to 0, we get a0 is equal to c1 plus c2 into 0, n is 0 into 1 raised to 0 plus 0 square into 1 by 2. So this term becomes 0, 1 raised to 0 is 1, c2 into 0 becomes 0. So a0 is equal to c1, and we are given a0 is equal to 2, so c1 is equal to 2. Okay, c1 is equal to 2. Is it clear? Now put n is equal to 1. Put n is equal to 1 in this equation. Let it be equation 2, okay, into. When we put n is equal to 1, then you get a1 is equal to c1 plus c2 into 1 into 1 raised to 1 plus 1 square into 1 by 2. Now this becomes c1 plus c2 into 1 is 1 plus 1 by 2. Isn't it? So we know the value of c1. We found out the value of c1. Okay, so that is equal to a1 is equal to 2 plus c2 plus 1 by 2. And here, I think I didn't give the value of a1, isn't it given? a1 is equal to, say, 3. Okay, the initial condition a1 is given to be 3. So you get 3 is equal to 2 plus c2 plus 1 by 2. Or you get, what is the value of c2? What is the value of c2? Find out the value of c2. 5 by 2 minus 3, isn't it? 5 by 2 minus 3. What will you get? What will you get? Minus 1 by 2, isn't it? You get minus 1 by 2, isn't it? 5 minus 6 the whole by 2. You get minus 1 by 2. Now I have found out the value of C1 and C2. Now substitute in general solution. Substitute in the general solution. You get AN is equal to C1 is 2, isn't it? C1 is 2 plus C2 is minus 1 by 2. So this becomes minus minus 1 by 2n into 1 raised to n plus 1 by 2 into n square. So whenever the initial conditions are given, the initial conditions are usually given to find out these constants. Find the constants. After writing the general solution, find out the value of these constants using initial conditions A0 and A1. Find value of C1 and C2 and substitute in the final solution. You get the answer. Okay. Is it clear? Is it clear? We had solved the homogeneous part separately. We had solved the particular solution separately. Finally, we added the two solutions, and using the initial conditions, we found out the value of constants C1 and C2 and substituted in the general solution. That is what we did now. Okay. Is it clear? Is it clear to you? Hello? This is solution of non-homogeneous recurrence relation when the right hand side is a constant. Okay. Say your attendance.
1.
2 absent.
2.
3.
4.
4. 5.
6.
7. 8.
9.
10.
11.
12. 13.
14.
15.
16. 17. Okay. 18.
18.
19.
20.
21.
23. Absent. 24.
24.
23.
25. 24.
23 present. 24.
26. 25.
Okay. 26. Next.
26. 27.
Okay.
28.
29.
30. 31.
32.
33.
34. Okay.
35.
36.
37. Absent.
38.
37, 38, 39. Next 40. Number 40. Absent.
41.
41. Okay. 42. Absent.
43.
44.
45.
46.
47.
48.
49.
50. Next 51. 51. Absent. 52. Absent.
53.
50. Next.
54. 55.
56.
57.
58.
59. 60. 62.
162. Next 63. Okay. So absent is number 40, 51, 52. Number 40, 51 and 52. Okay, thank you. 56%.